Hello APC Mechanics students in Unit 5 Rotation, Class 6 5.3, Newton's second law for rotation. Section 1, Newton's second law for rotation. A massive pulley of mass m and inertia I pivoted from its center is being acted by two balanced forces F1 and F2. Now here we have a massive pulley. And so the mass is being distributed from the center to the rim and it's being acted by two balanced forces F1, F2. The forces are being applied tangentially to the disc or the pulley. Now we call such type of pulleys to be a disc because the mass is being distributed uniform or is being distributed from the center to the rim. Now the magnitude of the torque produced by each force is given by F multiplied by R, which is 20 multiplied by 0.1, which is 2 Newton meter. Now why? Here I've mentioned that the force is being applied tangentially to the disc or to the pulley, and we know that the torque is given by plus minus Fd cosine theta. Because they are being applied tangentially, then theta is 0, which means that cosine theta is 1. Now the torques are being balanced, which means that 2 Newton meter minus 2 Newton meter, that would be 0, which means they are balanced torques. And that would be the pulley will preserve its state of motion either at rest or uniform motion, constant angular velocity. Now suppose the right force is increased, producing more torque from 20 newtons to 35 newtons. Now the force F2 again would produce a torque which is given by 20 multiplied by 0.1, which is 2 Newton meter. However, now that the force F1 will produce a torque given by 35 multiplied by 0.1, which is 3.5 Newton meter. These torques now are said to be unbalanced and they produce a difference of 1.5 Newton meter. This increase will cause the pulley to accelerate clockwise by net amount of what exactly? Now here, this amount would be related to 1.5 Newton meter. However, we cannot equate physical quantities with different units. We cannot equate a Newton meter with acceleration. And this can be done by implementation of a law, and for sure here we're talking about Newton's second law for rotation, which states that unbalanced net torque causes a body to accelerate. The value of this acceleration is the ratio of the net torque and the inertia. Mathematically, this can be done as alpha is tau net over alpha, or tau net is given by I multiplied by alpha, which is in complete analogy with F net is equal to ma. And let's perform this analogy between translation and rotation. So here we're gonna list some quantities related to translational motion. The force F is, so if we need to talk about its analogy for rotation, that would be the torque tau. The mass m, it will be upgraded to rotational inertia I. Acceleration A would be upgraded to angular acceleration alpha, and F net in this case. So if F net will be replaced by tau, so let me do it the following way. If F is replaced by tau, if m is replaced by I and a is replaced by alpha, which means that Newton's second law can be understood as an analogy of Newton's second law for translation. So let me repeat it again. Newton's second law for rotation can be understood by analogy from Newton's second law for translation, which is given by tau net is I multiplied by alpha. And let's solve a quick application or an example on what we have explained so far. Calculate the angular and tangential acceleration of the pulley given that its mass is given by 1.125 kilograms and the radius is 0.1 meters. Now here, because this is given by black, so this is a disc, then the mass is being distributed from the center to the rim. Such pulleys are called a disc. For this reason, we have provided that the moment of inertia of a disc is given by half mr square. Now, in order, the angular and the tangential acceleration can be determined by applying Newton's second law for rotation, but before we doing so, we need to utilize the forces that are acting on the disc or the pulley itself, and this can be done by, so previously we used to do it by an FBD, which is a free body diagram in which the object is being represented by a dot. But now, since we are interested in determining torques and the distances from the pivot point to the point of application of the force is important for us, we need to represent something called a rigid body diagram of the pulley, in which the body itself is being represented by dimensions. Now, what are the forces are acting on the pulley? We have the forces F1 and F2 as being shown in the exercise itself or the example. However, because the pulley has a mass, it will be subjected to the pull of gravity and the reaction at the pivot. Now we're gonna apply Newton's second law for rotation, which is tau naught is equal to I multiplied by alpha. Now what are the torques? We have the torque produced by G, R1 and 2. G represents the torque produced by the pull of gravity. Luckily enough, both forces, the pull of gravity and the reaction at the pivot, they produce no torque because their line of action passes through the pivot. Now we're left to determine the torque produced by the force F1 and F2. Usually we take the positive direction to be the counterclockwise. Here in this case, we're considering it to be in the clockwise direction. And again, we're assuming that the forces are being applied tangentially to the pulley, which is a disc. And remember that what is a disc? It is a pulley in which the mass is being distributed from the center to the rim, and that would be F1 multiplied by R, which is 300. Okay, so let's now replace them. Okay, tau is F1 multiplied by R, and tau 2 would be minus F2 multiplied by R, and let's replace them in this equation here, and we would have that this is F1 multiplied by R minus F2 multiplied by R. The moment of inertia is given by half mr square, and alpha in this case can be replaced by, so let me say that the tangential acceleration is given by the angular acceleration multiplied by alpha. Then alpha would be given by A divided by R, and we would have the following equality. Now here R cancels with the power of 2, so which means that F1R minus F2R is equal to half mr multiplied by A, and we can again cancel R. And now if we isolate for the acceleration A, then the acceleration A would be given by F1 minus F2 divided by half m. Now the values of F1 and F2 are given to be 350 minus 200, m is given by 1.25, and plugging that expression in the calculator we would get an acceleration of 240 meters per second square. This is a relatively large acceleration. You can always think about gravity, which is 10 meters per second square. However, apart from the tangential acceleration, we're also interested in the angular acceleration. The angular acceleration, remember that it's related to the tangential acceleration by the expression given by if A equals alpha R, then alpha is given by A divided by R. We have the value of A to be 240 and we have R to be 0.1, and that would give us 2400 radians per second square. And now for the rest of the video we're gonna solve some exercises on what we have explained so far. Exercise 1, a wheel of mass m which has a rotational inertia I and the radius r rotates with angular speed omega about an axis through its center. Retarding force F is applied tangentially to the rim of the wheel. Which of the following is equal to the magnitude of the angular acceleration of the wheel? And we know that the angular acceleration can be determined using Newton's second law. If this is a free response, we need to state properly that apply Newton's second law for rotation because this is a big law. Now for short, I'm not gonna do it, so tau naught would be I multiplied by alpha, and we're interested in alpha. Now the forces that are acting on the wheel, okay, we can have the mass, which is the pull of gravity, the reaction at the pivot, but they produce no torque. Since F is being applied tangentially, that means that F multiplied by R is equal to I multiplied by alpha. Then in this case, alpha is given by F multiplied by R divided by I, making B to be the correct answer. Now exercise 2, given the graph above of angular acceleration versus time for a rigid body rotating about a fixed axis, which segment of the graph represents the time interval during which the largest magnitude of the net torque is being exerted on the rigid body? We know that according to Newton's second law, tau naught is given by I multiplied by alpha. Then tau naught and alpha are directly proportional. If alpha is the greatest, which means tau naught is the greatest, and this happens in segment A. Now exercise 3, a solid disk of mass m, radius r, and rotational inertia I is free to rotate about a fixed frictionless axis that's perpendicular to the disk through its center as shown above. A force of constant direction and constant magnitude capital F is exerted on the disk. If the disk accelerates from rest, which means that the initial angular velocity is 0, at time t is equal to 0, through what angle theta does the disk rotate from t is equal to 0 to t is equal to capital T? Since the force F is constant, which means the angular acceleration of the disk is constant, and by that we can use the kinematic equations related to uniform varied circular motion given by theta is equal to theta 0 plus omega 0 t plus half alpha t squared starting from rest, and we're assuming if we're starting from the origin, then theta in this case is given by half alpha t, small t would be replaced by capital T squared. Now it's left to determine what is alpha, and this can be determined using Newton's second law for rotation, which is given by tau naught is equal to I multiplied by alpha. Now what are the forces that are acting on the disk? It has a mass, then it will be acted by the pull of gravity down, the reaction at the pivot up. They produce no torque, so you can just ignore them. And the only force that produces torque is given by capital F, then that would be F multiplied by R. And from the figure itself, it is apparent that F is being applied tangentially to the disk, then it's given just by F multiplied by R, which is equal to I alpha. Now in this case, alpha is given by FR divided by R. Now theta is half FR divided by I multiplied by T squared, and that would be FR T squared divided by 2I, making B to be the correct answer. Now exercise for the bar shown above is pivoted about one end and it's initially at rest in a vertical position. The bar is displaced slightly, and as it falls it makes an angle theta with the vertical at any given time as shown above. Which of the following graphs best represent the bar's angular acceleration alpha as function of the angle theta? Now in order to do so, we need to apply Newton's second law, and we need to understand what are the forces that are acting on the bar. Now the two forces that are acting on the bar are given by the reaction at the pivot. Let me assume it's something like that. And we have the pull of gravity. If this bar is homogeneous, which means that the mass is distributed uniformly, then the pull of gravity would be acting at the center of mass of the bar, which is at the middle. So that would be the pull of gravity acting downward like this. Now, alright, let's apply Newton's second law. Then tau naught would be equal to I multiplied by alpha. We can ignore the reaction because it produces no torque. Now the only force that causing the torque on the bar is given by the pull of gravity. Now if this is the pivot, then that would be the radial direction, like that, and the tangential direction would be something like that. Now we need to identify the angle theta between the radial direction and the tangential direction. If this is theta, then that would be theta, because here we're assuming that these are two vertical lines. And if this is theta, then that would be theta, and that would be pi by 2 minus theta. Now this is the angle here. So the projection of FG along the tangential direction would be among cosine pi by 2 minus theta, which give us sine theta. So the torque produced by the pull of gravity would be Fg multiplied by the distance from the pivot to the point of application. If this is L, then midway would be L divided by 2, and that would be sine theta, because let me explain again, it would be the cosine of this angle, which is the projection of Fg along the radial direction, tangential direction, which would give us cosine pi by 2 minus theta, which is sine theta, and that would be equal to I multiplied by alpha. Now the pull of gravity is given by mg L over 2 sine theta is equal to I alpha, and we're interested in the expression of alpha. In this case, alpha is given by mg L divided by 2 multiplied by I multiplied by sine theta. Here, as you can notice, that alpha can be written as a constant multiplied by sine theta. Now this constant would be identified by mgl over 2I. M is the mass of the bar and I is the moment of inertia of the bar about this pivot point. So we need to understand how theta is being plotted. Now the sine theta function, if we're starting from 0, it has the following shape. So for the first part of the region, that's the shape of the sine theta function, and if you compare, that means that D would be the correct answer. Now the bar shown above is pivoted about one end is initially at rest. Initially at rest means that the initial speed is given by 0. The bar is displaced slightly, and as it falls, it makes an angle theta with the vertical at any given time as shown above. Which of the following graphs best represents the bar angular velocity omega as function of time? Now this exercise is related to the previous one. First of all, we can directly do eliminations, eliminating this one because we're starting from rest, which means that omega should start from 0, which means it's either A or C or E. Now let's take a closer look. In order to understand which one is the correct one, we need to refer to the angular acceleration alpha. Now from the angular acceleration alpha, and after we know that the correct answer is given by D, we notice that as time evolves, theta is increasing and the magnitude of A is increasing. The magnitude, of alpha is increasing. Okay, so now we know that alpha is increasing, which means that if we refer to the first one, this is a straight line. This means that alpha is constant, and that's wrong because we know that alpha is already increasing. Now initially we have this is to be wrong and that to be wrong because we didn't start from 0, and that would be wrong as well. Now here in this case we know that omega and alpha are related via derivatives. We have theta omega alpha, so we apply here derivative. So alpha is the derivative of omega, which means that it can be understood from the tangent. Notice that here if we do the tangents, the slope of the tangent is decreasing, which means that alpha in this case is decreasing, making this wrong. However, if we consider this one and we consider the slopes of the curve at different points, we notice that alpha is increasing, which makes E to be the correct one. Now again, exercise 6, a solid disk of mass capital M and radius r is free to rotate about a fixed axis through its center. The rotational inertia of the disk around its center is given by mr squared divided by 2. So here we have that the mass is being distributed from the center to the rim. A force F is applied tangentially, a distance r over 2 from the axis. Tangentially means no need for an angle. The torque is simply just the force multiplied by the radius. The distance from the force to the center as shown in the figure. What's the angular acceleration of the disk? And this can be determined by implementing Newton's second law. Tau net is equal to I multiplied by alpha. For sure, the disk, it has the mass. It will be subjected to the pull of gravity and the reaction to the pivot, but they produce no torque. So that would be the torque produced by the force F, which is given by F multiplied by R over 2 because it's being acted at this point, and that would be I multiplied by alpha. Now I is given by half r squared multiplied by alpha. That would cancel, half would have to cancel, which means that F is equal to r multiplied by alpha, which means that F is equal to Fm divided by R, making F divided by mr, making C to be the correct answer. A wheel with rotational inertia I is mounted on a fixed frictionless axis. The angular speed omega on the wheel is increased from 0 to omega f. So we have from 0 to omega f an increase in angular velocity in a time interval t. What is the average net torque on the wheel during this interval? This can be determined by Newton's second law, which is given by R multiplied by alpha. If we're asked about the average of this quantity, then here in this case we're considering alpha average, and alpha average in this case is given by omega final minus 0 divided by capital T, which is omega f divided by capital T, and that would be I multiplied by omega f divided by capital T, which makes E to be the correct answer. Now exercise 8. A solid cylinder of mass m and radius r has a string wound around it. A person holding the string pulls it vertically upward as shown above, such that the cylinder is suspended in mid-air for a brief time interval delta t and its center of mass does not move. This is very important. Now the cylinder is not moving either up or down, so it's being held in its place, which means we have translational equilibrium. This is important, I will explain why. The tension in the string is capital T, and the rotational inertia of the cylinder about its axis given by half mr squared. The linear acceleration of the person's hand during the time interval delta t is given by what? Now we need to find the linear acceleration a of the person's hand, which is related to the angular acceleration alpha of the disk of the cylinder, and they are related to each other by a is equal to r multiplied by alpha. So basically, if we find alpha using Newton's second law for rotation, a is determined. Then tau naught is given by I multiplied by alpha. What are the forces that are acting on the cylinder apart from the tension? We have the pull of gravity, which is down. So, but basically the only force that produces torque is capital T. The pull of gravity does not produce torque because it passes through the center of the disk or the axis of rotation. Now here we don't have reaction because the axis of rotation is not being pivoted about any point. So that would be the force that only produces a torque is the tension, and it's being applied tangentially. So T multiplied by R is equal to I multiplied by alpha, and we're interested in determining alpha. Now I is given by half mr square. Now what about the tension? Notice that here there is a statement which is very important. The cylinder is being suspended in mid-air and its center of mass does not move, so which means that we are in translational equilibrium, and we can say that the pull of gravity and the tension are balanced forces, so mg is equal to the tension. Now the tension would be replaced by mg, so r is equal to half mr square multiplied by alpha. M with m would cancel, r with to the power of 2 would cancel, then g is equal to half r multiplied by alpha, which means that r alpha is equal to 2g, but we know that r alpha in this case is equal to a, so a equals to 2g, making b to be the correct answer. And finally, exercise 9 as an exit ticket for today's video. A disk initially at rest, which means that the initial speed is 0, is acted by a constant net torque of tau. The disk spins for a period of t seconds and rotates an angular distance of delta theta. The same disk is brought to rest. The disk is now acted by a constant net torque 2 tau. So at the moment the structure of the question is like that, which means that we need to apply the factor of change. Tau is equal to I multiplied by alpha. If tau doubles, it means that we have also doubled the angular acceleration alpha. The disk spins for the same period of t seconds. What is the new angular distance? The disk rotates. We know that. If we're starting from rest, delta theta would be half alpha t square, and if we apply the factor of change, that would be 1, alpha would be 2, and t would be 1 to the power of 2, that would be 2, which means that it's given by 2 delta theta, making D to be the correct answer. Then thank you for watching and see you soon in a new one.